Hello physicists! Today we're going to be having a revision lesson that is going to be focusing on energy, power and resistance. I'm going to be following the OCR Physics A specification. However, this video will be applicable to all exam boards. Okay, well, let's get started. We are going to start our revision by looking at energy first. The first aspect that we need to revise is the difference between potential difference PD and EMF. Potential difference is the energy that's been transferred from electrical to other forms per unit charge. EMF, on the other hand, is the energy that's been transferred from other forms, for instance chemical, as in a battery, to electrical per unit charge. What I'm going to also underline is the statement of per unit charge, which is incredibly important and it's often omitted when answering exam questions. Remember, in a simple circuit, for instance, we have a little cell that's been connected to a resistor. EMF we can find across this cell because chemical energy has been transferred to electrical energy. Potential difference we can define as the energy transferred across this resistor because we have electrical energy that's been transferred to heat energy across the resistor. We can summarize the two definitions with the following two formulae. For instance, potential difference is the amount of energy that's been transferred W divided by the amount of charge. And we can see how this definition really makes sense. It's the energy transferred from electrical, i.e. W, per unit charge. Similarly, for the EMF that's been given this epsilon symbol over here, this is the energy transferred per unit charge. We can also see why the per unit charge is a really important part of the definition because in a way this is half of our formula. Both of these equations indicate that our quantities are going to be measured with the same units. For instance, the unit for the potential difference or voltage is of course the volt, which is given V. For EMF, we're going to use exactly the same unit, which is the volt, once again given V. So both quantities are measured with the same unit. We can also rearrange the equations above for an expression for the energy that's been transferred. In the case of PD, this will be equal to the potential difference multiplied by the amount of charge. In the case of EMF, the energy that's been transferred will be the value of the EMF multiplied by the charge. While we are at it, let's also revise the base unit for the volt. Remember, the volt, as we've just said, is described as energy per unit charge. Now, a different way of writing this will be energy divided by current multiplied by time. We can really easily work out the base unit of energy. For instance, I would always just think of my favorite formula for energy. So I'm going to just use a half mv squared. The half is going to have no units. The mass will be measured in kilograms. V will be measured in meters per second squared. When I essentially square this, I'm going to get a base unit for the joule, or base unit for energy, being kg meters squared s to the power of -2. So this is the base unit for energy. The base unit for the volt, I can just say over here that a volt will essentially be equal to kilograms meters squared s to the power of -2 divided by amps and then divided by seconds as well. We can rewrite this as kg a to the power of -1 because it's at the bottom of the fraction, m to the power of 2, and s to the power of -2 divided by s is going to give us s to the power of -3, which is the base unit for the volt. We can use what we've learned about energy to calculate the speed of particles when they're being accelerated by a potential difference. For instance, over here we have a question in which an electron is accelerated by a potential difference of 5,000 volts. Knowing this, we can calculate the speed of the particle as it emerges out of the region of this potential difference. The way that we're going to do this is with the famous equation that EV is equal to a half mv squared. Let me just quickly demystify this equation. This is essentially electrical energy W, which is going to be said to be equal to kinetic energy. So this is essentially electrical energy that has been transferred to kinetic energy. Well, the electrical energy is equal to QV. Our kinetic energy is a half mv squared. Because we're dealing with an electron, our charge is just the elementary charge, so therefore we can see where this equation comes from. Now let's see whether we can use that to estimate the speed of this particle as it emerges out of the region of potential difference. All we need to do is rearrange for V, so V will be equal, V squared will be equal to 2EV divided by M, and then I'm just going to take the square root of this expression. Now let's plug in some numbers. So this will be equal to the square root of 2 times 1.6 multiplied by 10 to the power of minus 19, which is the elementary charge, multiplied by 5,000, which is the voltage that we're dealing with. Then we're going to be dividing this by the mass of an electron, which is 9.11 times 10 to the power of minus 31 kilograms. Let's put this into a scientific calculator. So calculating this, we are going to get approximately 4.2 multiplied by 10 to the power of 7 meters per second. Okay guys, we've actually revised the vast majority of the energy portion of this part of the specification. Now let's have a look at resistance next. Starting off with the very important definition that resistance is the potential difference across a component divided by the current going through it. R is equal to V divided by I. In this equation, R is the resistance, and this is measured in the units of ohms, like so. We can work out the base unit for the ohm just by the fact that resistance is essentially potential difference divided by current. We have already worked out the potential differences base units, which is kg, a to the power of minus 1, m squared, s to the power of minus 3. If you can't remember how to work this out, I suggest rewinding this video a couple of minutes where we did this just here. Now if we take this unit and all we need to do is divide it by the base unit of current, which is amps, and what we're going to get is kilograms. Now a to the power of minus 1 divided by a again is going to give us a to the power of minus 2, m to the power of 2, s to the power of minus 3 for the base unit. It's really important that you guys remember how to derive these, but please don't attempt to remember all of those symbols and powers. Talking about resistance, this brings us on to Ohm's law. Ohm's law states that in an ohmic conductor, the current is directly proportional to the potential difference at a constant temperature. Normally, Ohm's law breaks down if the temperature is extremely high. Mathematically, we can summarize this statement with V is equal to I times R, where V is the potential difference, I is the current, R is the resistance. We can investigate Ohm's law with the following experiment. All we need is a cell that we connect to a variable resistor, then we have another fixed resistor, and we have an ammeter in series and a voltmeter in parallel across the fixed resistor. First off, we will need to vary the resistance of the variable resistor. This will change the potential difference of the entire circuit. We're going to be measuring the current with an ammeter, then we're going to be measuring the PD, as we said, with a voltmeter. So once we had those readings, so we're going to take multiple readings in equal intervals of V and I. Then we'll be able to plot a graph of V against I. If Ohm's law is correct, the graph should be a straight line through the origin. Let's perform a y equals mx plus c analysis. So what I'm going to say is that V is equal to IR. Another way of writing this is R times I. Underneath, I'm going to write y is equal to mx plus C, and I'm going to add a little plus 0. We can see that this graph will be centered at the origin. Our intercept C is equal to 0, V is on the y-axis, I is on the x-axis, which means that in a V against I graph, the gradient, let's call the gradient M, is equal to the resistance. Let's have a look at IV characteristics next, starting with a resistor. First off, we're going to notice that the graph is a straight line through the origin. This would indicate that the current is directly proportional to the PD, which is on the x-axis. This means that the resistor will be obeying Ohm's law. Additionally, the resistance is constant as indicated by seeing no change in the gradient. Finally, you also see that the graph looks exactly the same regardless of polarity. In other words, the graph is still a straight line through the origin when the voltage and the current are negative. Hey guys, next up are the IV characteristics of the filament lamp. First off, you're going to notice that the graph is no longer a straight line through the origin. This means that the current is not proportional to the PD. In fact, the lamp does not obey Ohm's law. The potential difference is increasing at a faster rate compared to the current. This means that resistance is increasing. You kind of think of it this way, because R is equal to V over I. If the voltage is going to increase at a faster rate than the current, overall the resistance will be increasing. So the resistance increases, and this can be confirmed by essentially calculating R is equal to V over I across a few different points, should you need to do so in an exam. Additionally, the resistance will be increasing because as the current increases, so does the temperature, and there are going to be more collisions between the conducting electrons and the positive ions. Next up, we have the IV characteristics of the thermistor. Once again, the current is not proportional to the PD, the graph is not a straight line through the origin, and the thermistor does not obey Ohm's law. The current is increasing at a faster rate than the PD. We can see this by the graph almost wanting to curve towards the y-axis where the current is. Therefore, the resistance will be decreasing because I is going to be increasing at a faster rate compared to the PD. So this is opposite to the IV characteristics of a filament lamp. We could also confirm the fact that the resistance is decreasing simply by sampling a few points and calculating the resistance on them. The resistance will be decreasing because as the current and the temperature increase, the number density increases, so there are going to be more conducting electrons, and if there are more conducting electrons, the resistance will be going down and the current will be increasing. And next, let's have a look at the IV characteristics of the diode. First off, notice that they look very, very different compared to all the previous IV characteristics that we've looked at. First off, the PD is once again not proportional to the current, which means that the diode does not obey Ohm's law. However, this time the diode's behavior depends on the polarity. In fact, you're going to notice that there's no current when the PD is reversed. So this means that the diode will only be working if it's connected positive to negative. At point 1, the resistance is very high. In fact, it is infinite, and there's no current. At point 2, which is the point of threshold voltage, the diode will be starting to conduct. As it starts to conduct, the resistance decreases as the current rises at a faster rate than the PD. Once again, because R is equal to V over I, if the current is going to be rising at a faster rate, R is going to drop. This is one particular reason why diodes are so much more efficient compared to filament lamps. Above 0.3, the diode is going to have very, very little resistance. Next, let's have a look at resistivity. First off, the resistance of a material is not independent of the shape or length of the material. For instance, if I had a wire which was longer, it will have a higher resistance. So we know that resistance will have to be proportional to the length. Additionally, if the wire had a higher cross-sectional area, you'll be able to conduct more current, hence the resistance will be lower. So this means that resistance will need to be inversely proportional to the area. Now the constant of proportionality, which links those three quantities together, is known as resistivity, and that's given the Greek letter rho. Now, what are the units of resistivity? Let's rearrange this equation for resistivity, and what we're going to get is that rho is equal to RA divided by L. So the units for resistivity are going to be R is measured in ohms, A is measured in meters squared, and length is measured in meters. We can cancel those out, and what we're left with is that the units of resistivity are ohm meters. Let's apply what we've learned about resistivity to a little practice problem. So for instance, we have nichrome, which has a resistivity of 1.5 times 10 to the power minus 6 ohm meters. Calculate the resistance of a 1.5 meter wire with a diameter of 0.25 millimeters. Okay, well, we have the formula for resistance, and let me just write it once again over here. Resistance is going to be resistivity times the length divided by the cross-sectional area. A couple of things to be careful. I'm given the diameter of the wire, not the radius, and I'm going to be quite careful when I write down the formula for the cross-sectional area. So let's do this. This will be equal to the resistivity, which is 1.5 times 10 to the power of minus 6 multiplied by the length, which is 1.5. Now the cross-sectional area is given by pi r squared. I will need to both convert from millimeters to meters and additionally divide by 2, and also not forgetting the square. The reason for that is because the area is actually given by the equation pi r squared. So this means that r squared will be equal to 0.25 times 10 to the power of minus 3 divided by 2 and then squared. Now let's carefully input this into a scientific calculator. And this will give us 46 ohms. Let's have a look at an experiment to determine the resistivity of a wire. In order to do so, we're going to have the following circuit. We have a variable DC supply connected to an ammeter. Then we have this wire, which normally it's connected with crocodile clips to a voltmeter, the position of which could be adjusted along the length of the wire. For instance, we could have this length adjusted so that we're able to take the reading for the PD at different lengths of the wire. I normally also add a little resistor there, but this is just for safety to keep the current low to avoid the wire overheating. First off, before we get started and switch the circuit on, we need to measure the diameter of a wire with a micrometer and take multiple readings along the length of the wire. So this is really important. We don't just take a reading on one point, but we take multiple readings along the length of the wire. Then we take the average to reduce our percentage uncertainty. We're going to calculate the area using A is equal to pi d over 2 squared. In other words, pi r squared. This really is pi r squared. So let's write this like that. What we're going to do is we're going to vary the length L essentially by moving this wire across and taking the reading at a different length. And then we're going to be measuring the PD and the current with the voltmeter and the ammeter. We're going to calculate the resistance for each length, and we're going to be populating this table because R is equal to V over I, so we'll be able to calculate it at each point. We're going to plot a graph of R against L. Because of our equation, if this equation is true, the graph is going to be a straight line through the origin. This will allow us to calculate the resistivity because Y is equal to mx plus C. The graph is a straight line through the origin. R is on the y-axis, L is on the x-axis. What's left for our gradient is our resistivity divided by the cross-sectional area. So this means that, well, actually let's say that our gradient M is rho divided by A, which means that our resistivity will be our gradient A times the cross-sectional area of the wire. And now let's revise the dependence of resistivity on temperature. If we have a metal and we look at its resistivity, it is going to have a similar trend. First off, you're going to notice that the resistivity of a metal increases with temperature. The reason for that is because there are more collisions between the conducting electrons and the positive ions. Additionally, you're going to notice that the y-intercept is non-zero. The reason for that is simply because the material will still have some resistance at 0 degrees Celsius. If it didn't, we'll be able to have no resistance if we put a wire in a fridge or on a cold day. Okay guys, we've revised quite a lot of materials so far. Now let's go back to the basics, because we've discussed a lot about energy and even more about resistance. However, we have still not talked about power. So from your GCSEs, you'll be familiar with the equation that power is equal to V times I. However, if you remember, V is equal to IR, so this would mean that another way of writing out the power equation, rather than V, I'm going to write IR, which is going to give us I times I, so this will be I squared times R. Additionally, if I rearrange Ohm's law for I, let's do that. I will be V over R, and now I'm just going to substitute this in here, and what I'm going to get is a third equation for power, and this will be that power will be V times I, which is equal to V over R, so that'll be V squared divided by R. Those are the three main equations for power that we're going to be using in electrical circuits. Notice that the unit for power is the watt, which is given W. Don't confuse that with electrical energy. You should be really clear on what the unit of power is. Now, additionally, let's have a look at the one more equation for power, and that is that power is energy over time. In fact, I'm even going to use a word equation, which I almost never do. And the reason for that is because energy, electrical energy, is normally given the symbol W. That's because E is kind of reserved for electric fields, as we're going to see in the second year. But power is W over T. Rearranging this equation for W, electrical energy, we get that electrical energy is power times time, which can also be written as V times I times T. Those are the main power equations. Finally, we're going to be revising the kilowatt hour, which is the amount of energy used by a 1 kilowatt device in 1 hour. I want to stress that the kilowatt hour is a unit of energy. That's because 1 joule is actually a very tiny amount of energy. Here is where the kilowatt hour actually comes from. So electrical energy is power multiplied by time. So rather than just using watts, if the power is measured in kilowatts, and rather than measuring the time in seconds, if we measure that in hours, the amount of energy W then will actually be measured in kilowatt hours. But once again, I want to stress that a kilowatt hour is the amount of energy used by a 1 kilowatt device in 1 hour. If we know how many kilowatt hours we used, normally it would cost a certain amount of pence, and we can calculate the cost of electricity. Okay folks, we've done a huge amount of revision today. Well done for following this online revision lesson. We've gone through a lot of really good and interesting material, so well done for following this. If you found this video useful, please give it a like, and yeah, thank you very much for watching, and I'll see you in the next video.